All right, so let's see what we have here. So we got models of the atom practice sheet here. We're doing the Bohr models this time rather than the J.J. Thomson. Rutherford is in between these two, so just remember that Rutherford's gold foil experiment helped pave the way to the discovery of the nucleus, where the majority of the mass is now in a very small amount of area. Not the majority of the charge, remember, because the charge is split between positive and negative within an atom, and they're both pretty much equal. So the negative electrons and the positive nucleus. Okay, so using this diagram on the side, this is just for the same diagram you've probably seen in our notes for a hydrogen atom. Determine the wavelengths of the visible emission spectrum lines of an excited atom. Okay, so we got a ground state down here at negative 13.6. These are electron volts. So that's not excited. But if an electron was up in state 1, 2, 3, or sorry, 2, 3, 4, 5, all the way up to 6 here. Is it 6? 2, 3, 4, 5, 6, yeah. The atom would be excited. And then when the atom would drop, or that electron would drop down, it would release a photon. Now, what I know already, if I drop from state 1 down to ground state, that electron volts is too high, right? So what I know, if I were to go through this and say, okay, what are my numbers that I could have for a visible spectrum inside this hydrogen atom? It's in that Balmer series, I believe it was. Well, I probably just want to figure that out. I'm just going to put on this side here. I think we had the numbers somewhere. We did the notes somewhere. I think we did it one of the other question sheets, one of our assignments, where I asked you what are the energies of visible spectrum. So if I were to go from like 400 to 800 nanometers, and this is the visible spectrum here. That's in nanometers. That's so ugly with an N there. Let me just fix that. Okay. So the energy at the 400, we're just going to use HC over lambda. Negative 15 times C over lambda. I get 3, well, I have this number. I've seen these numbers before. 311 electron volts. And if I do it for the 800, we'll just change this to an 800 here. I get like approximately 1.55 electron volts, or 1.7 or so. Right. So as long as my energy jump on my diagram there, that's just below my head here, as long as my energy jump is somewhere between those two numbers, I would have a visible spectrum. So the energy jump from -3 down to -13, that's 10. So that's too large. So that's going to be ultraviolet. So I just go through and just determine which of these are going to be visible spectrum. So I know it's not going to be a jump down to 1. So let's try a jump 2, or sorry, not 2 to 3, so 3 to 2. Okay, so the jump 3 to 2, which would be from the 1.5 to the 3.4 there, I would just have to find the difference between those two. So 1.5 minus the -3.4. So that difference would be 1.9. And 1.9 lands within our spectrum here. So 1.9 electron volts. So that one there's going to work for us. That's not going to answer the question because we still need to determine the wavelengths. What if I go from 4 to 2? Let's just go up a little bit higher. So if I go 4 to 2, so that's going to be 3.4 minus the 0.8. So this is a 2.44, or 2.55, sorry. So that's going to work for us. What if I go 5 to 2? So 5 to 2 would be 3.4 minus 0.54. Yeah, so that's going to work. That's going to be 2.86 electron volts. That's going to be in the visible spectrum. What about 6 to 2? So getting a little bit large here. So 6 would be 3.4 minus 0.38. So 3.02. That actually might work out for us. 3.02 electron volts. That could fit within my spectrum. If I'm assuming 400 is my end. So that's all the way down to 2. Seems like that's any transition down to 2 is going to give us a nice little visible spectrum. Let's do the next one here. Let's just double check. If I go from 4 to 3. Okay, 4 to 3 is a pretty small little gap there. Just one second. Okay, so 4 to 3, it's going to have a energy difference of 0.6465, sorry, electron volt. That's not going to work. I'm going to skip past 5 to 3. I'm going to go right to 6 to 3 because that's going to be the biggest jump there, and the biggest jump gives us more energy. So hopefully, maybe this will work. We'll see. 1.5 minus the 0.38 at the top there. I'm going to get 1.12 electron volts. Okay, so that's not going to work. Okay, so these are the only 4 that are going to give me the visible spectrum here. Okay. So what I'm going to do now is I'm just going to change these into wavelength. So I'm going to use the formula HC over lambda. So I'm just going to go HC over E. I'm going to do it a bunch of different times. I've got 4 different of these. So I'm not going to show the work for all of these, but I'm just going to do the 4 different times here. I'm going to calculate really quickly, because I could just replace the numbers, make it a little bit easier myself. Remember to use the H value that corresponds to electron volts. And okay, so my first one, I'm going to put in nanometers, is going to be 654 nanometers. My next one is going to be 2.55. It's going to be 487 nanometers. My next one's going to be 86. It's going to be 434 nanometers. And my last one, I'm going to use the 3.02 there. It's going to be 411 nanometers. There we go. Those are all the ones in the visible spectrum. They're the Balmer series too, so I knew that from the notes. Okay, next one here. Why do transitions in hydrogen atoms emit infrared when they go down to 3 and ultraviolet when they make a transition to 1? Well, I kind of showed it here. It's just that the jump is too small, right? If it's too small, you're not going to have enough energy, and the jump is too big because the biggest jump from 2 to 1 is, this is for the second part here. The jump from 2 to 1 is 10.3, is it? Somewhere about that, 10.2 or so. 10.2 electron volts, which is already in the UV range. Therefore, any jump to 1 will be 10.2 electron volts plus a number, right? Which, oh, actually, I'm going to write that differently. Will be always greater than, that's a better way to say this, greater than 10.2. Okay, that's the reason why it's always ultraviolet. And then you could probably say and you jump down to level 3, since the largest jump, which is 6 to 3, is only 1.12 electron volts. Any jump to state 3 will be less. I'm going to highlight this, less than 1.1 electron-volts. Okay, cool. Helium laser produces a photons of a specific wavelength when it drops from an excited state to a lower state. What is the energy difference between these two states? Okay, that's pretty easy. If I drop down and I release a photon, that photon must be the same energy difference. So I'm just going to calculate what the energy difference, or the energy of the photon is. And then that's the energy difference. It's a pretty easy question. So I'm just going to use, because it says use electron volt, so I'm going to use the electron volt number right away. So I get a 1.96 electron volts. Okay, so here we got a bunch of atoms, or for mercury here, a bunch of states for mercury from 1 to 6. The numbers are backwards here, so they're not telling us the top number here, so I'm not too concerned about that though. An atom de-excites. They're close. Let me just read this over here. It de-excites by having one electron drop from a series of energy levels. This process is called fluorescence. It is often seen when high energy photons such as X-rays or ultraviolets excite the atom, which then de-excites to a lower level wavelength emission. That's how fluorescent lights work. A common example of fluorescence occurs in the colors produced when rock and minerals. Well, there's a lot of useless information here. Yeah. Okay, so the wavelength of a photon needed to excite mercury from its ground state to state 5. So this is state 5 here. So the question A, I'm going from ground state all the way up to there. So the energy here is going to be 8.85 electron volts minus 0 electron volts. So this is the energy, which is 8.85 electron volts. So it's outside the visible spectrum for sure. What do they want? They want the wavelength. So I'm going to use the HC over lambda formula to do this. It's electron volts. I'm just going to use that number again. It's fun because I can just keep on reusing what's in my calculator here. I get a wavelength of 140 nanometers, which is definitely in the UV range. What is the longest wavelength of photon that will be emitted as mercury de-excites? Well, a lot of people say, oh, the longest photon would be the longest gap. No, but the longest gap is the most energy, which is the least amount of wavelength. If I want the longest wavelength, it's going to be the smallest gap, or the smallest change. So when it de-excites, that's going to be B there. So it's going to be between 6 and 5, which is going to be, I don't want a negative number. I'm going to go back the other way. So 9.23 electron volts down to 8.85 electron volts. So the energy of the largest wavelength with the least amount of energy. Remember, they're inversely proportional to each other. So it's 0.38 electron volts. That seems familiar. That's the number we had before. And the wavelength, I'm just going to go HC over E again. Oh, hey, look at that. I have this again. I just pull that up. Right there. 0.38. The longest wavelength is going to be, you put this in nanometers, I guess, 3,000 268 nanometers. I'm not too concerned about sig digs there. The number of possible transitions here. Okay, so I'm not going to count my transitions. I would just start by drawing them. You could draw them like you draw this series. You would go, you draw them as if you're going down to the first level. And I'm going to keep on doing that all the way down to the first level. Okay, so there's 5 there. Okay, I'm going to add on the next one. So I'm not going to go down to 1 now. I'm going to go down to 2. The next one's going to go from here to 2. And you probably guess right away that there's going to be 4 of them there. Okay, and then I'm going to do it down to 3. Let's use red here. So there's going to be 3. You try not to overlap them. And let's do a couple more here. So I'm going to go down to 4. Obviously, that's 2 more. And then my last one is going to be 1 more. So I'm going to add all those together. You get all my transitions. 5 plus 4 plus 3 plus... Hey, it's 15. Okay, the last one here. If an atom has 100 possible energy transitions that are very close to each other, okay, what would the spectrum produced look like? So this is just talking about, like, will they have nice little thin lines, or will the thickness of that line be be wider? Because if they're really close to each other, they're going to look pretty close, but they're going to be a little bit off from each other. So there's going to be kind of a little bit of space between them. So the spectrum at that energy transition will look thicker. There we go. Cool. So that's why you see in, say, a spectrum emission diagram, some of the lines look thicker than others, just because there's a whole bunch of transitions that are really close to each other. Yeah, there we go. Okay, I'll see you in the next video. Bye.